Good morning, ladies and gentlemen. My name is Surush Surushan, President of the Hydrology Section. On behalf of AGU, I welcome you to the first union session of the Spring Meeting 2000. And the session, of course, is the linking of hydrologic sciences and water policy in the 21st century. Of course, this particular program is co-sponsored between Hydrology Section as well as the Committee on Public Policy. And following this morning's keynote talk by Dr. Neal, then we will move into Hydrology session, which follows exactly at 10:05. To start this session, I just wanted to emphasize that how pleased we are as members of the Hydrologic and Water Resources community to see that issues related to water and water resources are getting the highest level of attention at both the U.S. government and abroad. And of course, to sort of set the context for Dr. Neal Lane's talk, I would like to have a couple of transparencies. If the other one could be shut down, or maybe you can use the other. Well, okay. The issues, I will try to sort of focus on the western U.S., southwest. This, of course, is the Colorado River Basin, and the graph at the bottom is the hydrograph, water measured in the river at Yuma, just before it enters Mexico. You see from a certain point, there was a pointer here which disappeared, but anyhow, there's a certain point which is about 1962, which coincides with the completion of the Glen Canyon Dam, that most of the water in the basin is completely utilized. And so pretty much if you look at sustainability of water, since 1965 onward, we have been very much using all the water resources on this basin, except for the years we have El Nino or La Nina that certainly we have a little burst of flooding that give us additional flow in the river. And of course, in terms of the quality, we go from the upper basin, 55 parts per million of salt concentration, to about 800 parts per million of salt concentration. If we also look at sort of the groundwater issue, and again, the Southwest experience, this is a location, Eloy, somewhere between Tucson and Phoenix, and the land surface in 1952 happened to have been over there. And as you see through the years, because of overdraft of the groundwater, we have seen a rather unsustainable situation developing, which is not really unique into this particular area, but many locations in the Southwest U.S. Well, part of the impact of this, of course, is on the delegate riparian zones in our region. And this is a river near Tucson, Arizona, Santa Cruz, 1940. The groundwater used to be high enough that part of the year we used to get a little flow in the Santa Cruz, and therefore it was a nice picnic area. And by 1975, you see, because of the overdraft and groundwater pumpage, the riparian zone has pretty much disappeared, and this is a primary concern in most areas in the Southwest and perhaps other regions of the world. Well, if we look at both sources of water, surface and groundwater, then if this is the situation at the current time, the population is expected to grow by another 20 million to 64 million by 2025 in the Southwest U.S., and 4 of the fastest growing states in terms of the population happen to be in the Southwest U.S. So obviously there is a question about how could it sustain the type of demand for water that are expected to even increase, and yet with the current supply and availability of resources. The situation is not unique to the U.S. This is the flow out of the Yellow River Basin in China into the sea. As you see, from 1972 to 1998, these bars represent the number of days that there was almost no flow taking place and flowing into the sea. So you see that from 13 days in 1972 to 280 days in 1998. shows a dramatic decline in the amount of flow in the river that is being consumed to maintain the requirements of the population. So the point is that obviously this is not unique to the U.S. It happens to be in China and many other parts of the world. And as we look at the water cycle and the uncertainties and variabilities due to climate change and other aspects, that if we put all the waters in the world in this big bottle that we are all familiar with, the total amount of fresh water will be in that spoon, and most of it is, of course, in the form of ice. So the question becomes one of how do we deal with this water issues for the next century. And we are delighted that Dr. Neal Lane accepted our invitation to come here and perhaps give us a perspective of the U.S. on this issue. And Dr. Lane does not really need much of an introduction. He actually has a very distinguished career and one of the leading authorities or members of the community in terms of science, technology, and policy. Provost of Rice University, after that became Chancellor of University of Colorado at Colorado Springs, moved to direct the National Science Foundation and served on the board, National Science Board, and presently he's the Assistant to the President for Science and Technology and Director of White House Office of Science and Technology Policy. I'm pleased to have Dr. Lane, who will give his half-an-hour presentation, after that followed by questions and answers.
Thank you very much. Thank you very much, Sarush. Good morning, everybody. Pleasure to be with all of you. It's good of you to show up after a long holiday weekend. When the sun finally is going to come out, I think, if predictions are correct. When I learned that you were going to talk a little bit about science and engineering, technology, and public policy, I didn't want to miss the opportunity to meet you and talk with you a little bit about some things that are so close to what we talk about, what we work on in the White House. So I really appreciate this opportunity. The scientists and engineers, I think, have a unique and certainly extremely important role to play in the policy arena, maybe more so than we as researchers generally recognize. But we also don't usually make our voices heard, not nearly to the extent that I think is necessary, and that's part of what I want to talk to you about. It's a little bit like a story you may have heard about a salesman who made a random phone call to a home. It goes sort of like this. Salesman calls, voice of a little boy answers the phone and softly says, "Hello." "Is your mother there?" the caller asks. "Yes, but she's busy," came the reply. "Well, how about your dad? Is he there?" "Yes, but he's busy too." Well, now the salesman's curiosity is getting piqued, which is okay with me if you've had salesmen on the phone, but wondering what they were doing. "Is anybody else there?" "Yes, there's a fireman." "Well, can he come to the phone?" "No, he's busy too." "Is there anybody who can come to the phone?" "Well, there's the policeman, but he's busy talking to my mom." Well, the salesman can't take it anymore, and so he asks, "What are all those people doing at your house?" In a very soft whisper, the reply came, "They're looking for me." Well, there are times when we scientists are a little bit like the mischievous boy. We tend to force the policymakers, who generally know very little about science and technology, to try to extract from what we're saying and what we're writing some essence of application or relevance so that they can use the information or they can convey it to folks on the Hill or in other ways let it inform policy. There are a lot of exceptions to this, and it certainly doesn't apply in any unique way to your science community, but it's a much broader issue that we need to wrestle with. I think in the years to come, it's clear that the most vexing national and international issues, including natural resource problems, will require a more sophisticated technical understanding and a higher level of communication between scientists and engineers and managers. AGU's decision to highlight the link between science, technology, and policy is a big step in the right direction, and I congratulate you for that. Now, I want to return to the topic of science, engineering, technology, and public policy at the end of my remarks, but first let me make clear the Clinton-Gore administration's continuing commitment to investment in science and technology. I'll spend a few minutes describing our balanced R&D budget portfolio, and then I'll focus on one element of that portfolio, a very important one, and that's research on global water cycle. I hope you would find that of particular interest. That new initiative on the global water cycle illuminates the close link between science and technology and public policy and the need for scientists and engineers to become civic scientists or citizen scientists, full participants in the political process. As many of you already know, President Clinton and Vice President Gore have proposed a record-setting science and technology budget for Congress for fiscal year 2001. The centerpiece is a nearly $3 billion increase in what we call the 21st Century Research Fund. That's roughly the whole fundamental half of the R&D activities supported by the federal government. This fund, the Research Fund, I'll call it for short, includes all of NSF, all of NIH, essentially all the science technology programs of NASA, NOAA, and the other agencies, including basic and applied research of the DoD services. It is simply a way to look at that whole chunk of the science technology budget, which clearly is a forward-looking investment in the future, and keep track of how the money is spent. It doesn't mean that the budgets have been shifted around or that agencies have been reorganized. It's just a way to try to get Congress to focus on what we think is essentially 100% investment. Good way to spend Americans' taxpayers' money. This research fund funds also the stream of innovation that ensures, we think, continued prosperity in the 21st century. Finally, the budget that the President and Vice President have sent to the Congress begins to restore the balance between biomedical research and the rest of the R&D portfolio, a balance that we believe underlies progress toward national goals such as promoting long-term economic growth and high-wage jobs, sustaining healthy, educated citizenry, enhancing national security and global stability, and improving environmental quality. Those are important, very large, very demanding national goals. They all have science and technology foundations. The FY 2001 budget request for R&D continues the important R&D trends established by the President and Vice President, and it raises the bar a bit. This is the 8th consecutive year that the President and Vice President have proposed increased investments in civilian research and development. Civilian R&D is up 43% during this administration. That's roughly double the rate of inflation, CPI inflation, over the same period of time. In the fiscal year 2001 budget, the 21st Century Research Fund grows by 7%. The President's budget boosts funding for basic research with a $1.3 billion increase, 8% increase. Funding for basic research is up 52% since 1993. R&D support to universities will increase 8%, an increase of $2.1 billion. R&D support to universities is up over 50% since 1993. And perhaps most importantly, this budget substantially improves the balance in our R&D portfolio in recognition of the interdependence of scientific disciplines. Harold Varmus was very good in speaking to this issue when he was director of the National Institutes of Health. He pointed out if you don't support the underlying physics and chemistry and mathematics and computer science, various fields of engineering and physical sciences, you won't have the tools necessary to advance biomedical research and do all the other extraordinary things that this nation needs. President Clinton has also spoken several times about the importance of balancing the R&D portfolio on several occasions this year. It's especially significant that the President's R&D request contains increases for university-based research that will ensure a strong science and technology workforce in the 21st century that will help close the opportunity gap and provide economic opportunity for all Americans. It also assures for the immediate future the U.S. position as a world leader in science and technology. We can't give that up, or all of the other things that follow will suffer. The administration's actions over the past 7 years have helped to sustain America's ability to create and capitalize on world-class science, engineering, and technology. President Clinton and Vice President Gore funded increases in the federal and research and development budget, even as we steadily brought the budget into balance and ultimately to its record surpluses of today. The R&D budget has actually grown as a percentage of total discretionary spending, a clear indication that this administration considers investment in science and technology a high priority for the nation. And the administration's strong fiscal year 2001 budget request for science and technology is unprecedented. So where do we go from today? Well, at the beginning of their administration, Bill Clinton and Al Gore proposed a national target for research and development, public and private expenditures, everything we invest in R&D. They said it ought to be about 3% of the GDP. At that time, it was about 2.6. 3 really looked like a very ambitious target. Well, we're almost there. That's largely due to increases beyond what the federal government was able to do, increases in the private sector that were made possible by a healthy fiscal climate and by the R&D tax credit. Well, we think it's time maybe to stretch ourselves a bit more, particularly with respect to federal funding. This spring, in a number of forums, I proposed a target not for total federal R&D, where the defense development needs very often influence the larger number in ways that depend particularly on the defense mission. So we think maybe it's a good idea to look at this sort of fundamental half of the federal R&D portfolio, this thing we call the 21st Century Research Fund. That fund, which includes NIH, NSF, and all the science technology programs of the other agencies, is currently funded at just under 1/2 of 1% of GDP. In 10 years, that really ought to double. We ought to get on a new trajectory that doubles that fundamental half of the federal R&D portfolio in a period of 10 years or so. We can argue about exactly what the percentage should be. People ask me, why should it be double? Well, why not? I mean, yeah, double sounds good to me. I think the point is, I don't mean to make light of it, the point is it's so clearly a good investment that just like in your own household finances, if you know it's a good investment, if you know the payoff is high for your family, and in this case for the country, you really ought to invest as much as you can afford. We as scientists can't decide how much the nation can afford in any one category. The political process has to do that. But we need a target out there. We need to talk about what it ought to be, what we would get out of that kind of investment, and then enter the debate when the budgets get put together. We need to put federal research funding on a new and steeper upward trajectory of balanced investment, because it's a balanced investment in America's future. Now, this idea might receive some bipartisan support. Former Speaker Newt Gingrich, who's been a strong advocate for science and technology throughout his career, and he'll speak later today, I believe, he wrote an op-ed in the Washington Post a while ago, you may have seen, calling for a 20% increase in all areas of scientific research and a doubling in 5 years. Well, that would be difficult to do, but I like Newt's bold thinking on this matter, because as a nation, we simply can't afford not to increase our science and technology investment, even as we keep the budget balanced. Now, many of you may already know that Congress hasn't gotten off to a great start on meeting the President's science and technology budget request. Last week, the House passed a bill that cut the request for NSF by $508 million, and the request for NASA by $322 million relative to the President's request. The Senate's VA HUD subcommittee, as we call it, that's the committee that has in it Veterans, Housing, Urban Development, NSF, NASA, FEMA, EPA, and a number of other agencies. It's one of the biggest appropriation bills in the 13. That stingy allocation has been pilfered to some extent. They really, on the Senate side, they can't even write a bill. And I thought that the appropriation chairs have spoken out really pretty clearly on that matter. It's not too late for you to make your voices heard on behalf of a strong science and technology budget, and I hope you'll emphasize the importance of a balanced R&D portfolio. The administration's proposed R&D investments will enable the science and technology agencies to achieve all the President's national goals of science and technology and do all the other things we know are so important. There are far-reaching, these goals are far-reaching and ambitious goals that I referred to earlier. We also must set priorities among the various ways in which we might make these investments. Many interesting and important research questions to be addressed, so where do we put the money? Well, today I want to talk to you about a new initiative, the one on the global water cycle, that promises to advance our progress towards several societal goals. Life, as we know, depends on the global water cycle. Fresh water, which sustains terrestrial ecosystems and human existence, is delivered to the continents by the water cycle. Assuring adequate supplies of fresh water is at the heart of one of the greatest human and scientific challenges, which is to achieve sustainable development of our natural resources. Former Norwegian Prime Minister Gro Brundtland gave the most widely accepted definition, I think, of sustainable development in the report Our Common Future. He said sustainable development is meeting the needs of the present without compromising the ability of future generations to meet theirs. When it comes to water, we're not achieving this right now. The knowledge that water cycles from the sea to land has been known for thousands of years, but we do not know enough about how the cycle works to alleviate the problems of shortage or overabundance of clean, fresh water. We don't get enough or we get too much. Consider the current situation. We recently marked the birth of the world's 6 billionth person, and we project the population will reach 9 billion by 2050. Already 2 billion people lack access to fresh water and basic sanitation. The world's supply of fresh water is not increasing, so per capita availability of water will inevitably decline. Our need to understand the variability of the water cycle underpins our economic prosperity and our capability to cope with famines, floods, and rising seas. And the challenges of water management are not confined to the developing world. The American West provides an equally compelling example. At the turn of the last century, the initial settlement of the West was just underway in many states. The scientific information needed to support the policy of Western water law, the doctrine of first in time, first in use, was not especially demanding. Simply measure the flow in the streams and divide it up according to who filed first. Now the problems are much more complex and the debate about the highest and best use of water more polarized. Surface water is now recognized by the Arizona Supreme Court as being inextricably linked to groundwater. Many communities in the West are mining groundwater, a practice that can't be sustained. Some Native American tribes claim flows that existed prior to European settlement, therefore predating any measurements. Endangered species of plants and animals share the same hydrologic flow system that supplies water to municipalities and rural areas, pitting values against one another. The future holds the possibility of bringing more difficulty to an already complex situation. We know the water cycle helps determine the Earth's climate, and we expect climate change to bring about changes in the water cycle. In fact, there's some evidence that climate change is already causing shifts in the water cycle. And when we look at vulnerability, as we are in the nearly completed assessment of the impacts of climate change for the United States, it turns out that water, whether too much or too little, or at the wrong time, is a major factor in nearly every region of America. Well, it's no exaggeration to say that we're vulnerable to water cycle extremes right now. Floods and droughts, including Hurricane Floyd in 1999, the Mississippi River and Midwest flooding in 1993, and Hurricane Andrew in 1992, constitute some of the most costly natural disasters in our history. By 2010, 3/4 of the U.S. population will live in coastal areas, making our nation even more vulnerable to hurricanes and floods. This slide shows a number of weather-related disasters on the vertical, costing $1 billion or more by year across the bottom here. And certainly in this period, in some of this period, you may recall, we were exceeding a cost of $1 billion a week. This is a highly variable situation across time. Fortunately, it was not $1 billion a week for the last several decades, but that gives you some measure of what we're about. Clearly, we have to improve our capability to deal with extreme events today and build some resiliency to cope with an increase in these events as the climate changes over the coming decades. Current researchers believe that even a slightly warmer atmosphere will accelerate the hydrologic cycle by increasing evaporation, by and total precipitation. I mean, to the physicists, it's sort of what goes up comes down. I know it's more complicated to you folks who understand water, but it obviously makes sense. You raise the temperature a little bit, and you put more of the ocean's water in the atmosphere, and that's going to come out. The question is, where does it come down? When does it come down? At what rate? We need to understand much, much more about this situation. Globally, precipitation has increased 1 to 2% over the last century. This map, which is a map of the world, it's a little hard to see the colors, I think. There are green colors, which are wetter areas, and there are brown colors, which are drier areas. And let me just see if I can point. These actually are brown in here, and the message of this slide across the world is roughly as follows. The wet get wetter and the dry get drier. And these Sahara regions, for example, and even some of the islands down in the lower, just below Florida here, and then in various localized places throughout much of Europe and the United States, we're in for some droughts. And then just as severe flooding is predicted for other regions, sometimes not so terribly far away from the droughts. For the continental United States, which we show here, the average precipitation has increased 8% over the last century, as air temperatures have increased 1 degree Fahrenheit. The upper Midwest and the far west have particularly become wetter. We can, I think you can see there is some green here. That is wet and that is dry. Here's Texas. You'd expect some dry in Texas, I think. Here's sort of where my roots are planted down here. Around Houston, looks like it's going to be a little damp. So I'll certainly get ready for that. That's where I end up. Also, we have some evidence that precipitation is being delivered by storms with greater intensity in recent years relative to early decades of the 20th century. If climate changes the way that most researchers expect, we'll see an increase in the incidence of extreme downpours and in both floods and droughts over the next century. Well, these changes in the precipitation regime will have major consequences. The last decade has shown that extreme events are not completely random, but driven by climate forces that we're just beginning to understand. We have a great capacity to manage water resources, but if the last 100 years of experience are not a good surrogate for the future, then our commonly accepted engineering tools for design of bridges, culverts, and floodplains, our nation's infrastructure, are becoming less useful, perhaps even obsolete. Changes in the water cycle also will affect the amount of fresh water in storage. The great stores of fresh water and snow and ice, groundwater, and rivers and lakes are all likely to undergo changes in the amount, timing, and availability of the water. Our understanding of the fluxes in and out of these reservoirs is in inverse relation to their amounts. The availability of fresh water has implications for all of our national goals, for the economy, to health, to environmental quality. And the potential for problems caused by changes in the water cycle are enormous. For example, surface water, lakes, rivers, and reservoirs, accounts for less than 1% of the total fresh water in the world. The increasing cost of construction, fiscal restraint on government spending, the few remaining sites favorable for reservoirs, and increasing concern for the environment have forced water managers to rethink traditional structure-based approaches and experiment with new ones. The storage created by dams and reservoirs on the nation's rivers has reached a maximum. Not clear where we could store any more water. As climate changes, snowpack will melt earlier, and for example in the Pacific Northwest, capacities could well prove inadequate to supply hydropower, salmon habitat needs, and agriculture and municipal water supply needs. We need to understand better the fluxes that are at work in the Great Lakes, our nation's largest freshwater body. With lower precipitation and without winter ice, the Great Lakes have declined rapidly in the last 3 years. 3 years. The lakes may reach their lowest levels later this year, since we began record keeping in 1860. The USGS and the Joint International Commission are proposing new work next year on the Great Lakes in response. As the President said in his recent trip to Michigan, we must understand why the lakes are dropping. About 25% of the fresh water in the world, 95% in the United States, is stored below the land surface. Groundwater is our nation's largest reservoir of fresh water. However, broad-scale depletion of regional aquifers has occurred just in the last half of the 20th century since the advent of submersible pumps. Land subsidence in Arizona, which is shown here, actually I think it is the pink that shows the subsidence, is that right? And the other color shows the dropping of the water level by 100 feet or so, if I have it roughly right. It's obviously caused by overpumping and reduces an aquifer's storage capacity once the ground moves down. A key future challenge is to make use of this storage capacity conjunctively with the surface water. We need to know more about our groundwater reserves, how they change in response to climate variation, and their capacity to store more water. Most, 75% of the fresh water in the world is stored in glaciers and the polar ice caps. There's evidence the glaciers and polar ice are melting. As the temperatures rise, we cannot discount the possibility that the ice caps will also begin to melt. This is important because they play a crucial role in the climate system. For example, it's believed that the release of fresh water to the ocean has the potential to disrupt the thermohaline circulation of the oceans. These ocean currents are the conveyor belt that transports warm water from the equator polarward and in turn controls continental climate. So if we shut that warm water off, then the situation gets very different for our coastal regions. Indeed, the situation in London, I think, would not be so terrific under those circumstances, worse than I think in Dickens' time. There, of course, is evidence that this circulation has shut down in the past, so this is not in any way a scientifically impossible situation. But we don't, by any means, understand enough about the dynamics here of this very complex system to say. These concerns are resulting in the emergence of water cycle research as a priority in the U.S. Global Change Research Program. The President has proposed $308 million in fiscal 01 for research on the Earth's water cycle. George Hornberg will talk more about this particular initiative and as a part of the Global Change Research Program in session 3 this morning. This represents a $35 million increase, a 13% increase over last year. But there's much important work done outside the U.S. Global Change Research Program and other government agencies and at regional, state, and local levels around the world. So we need to do more to coordinate and integrate all of these efforts. Looking to the future, I think there are 3 steps that we must take on our own and in collaboration with other nations to work towards sustainable development for water and other natural resources. First, we must increase support for research and monitoring to better understand the Earth's systems, our relationships to water, including water use, and storage replenishment, climate change, and means for water management at the global, regional, and local levels. Today, the administration is investing over $5 billion annually in environmental and natural resources research. We've had mixed success in obtaining funding from Congress for these programs, but we will continue to work at it with your help. Second, we must use information and telecommunications technology to improve our tools for science and engineering. Advances in remotely sensed observations of the land, oceans, and atmosphere, and the use of such observations in more sophisticated models may initiate some important changes in the conceptual basis of hydrology. Finally, we need to develop and test new technologies. For example, highly efficient use of water for irrigation and municipal needs, the development of new waste treatment in which zero discharge of pollutants occurs, and new water reuse technology. Well, I've only touched on a few of the issues, and they're issues you know better than I do, but I hope they might serve to highlight what I think is a fact, that we cannot reach the goal of sustainable water resources without a major effort from science and technology and from the science and technology community. But my most important point is that this alone will not be enough. We need to engage the decision makers, the concerned citizens, and other stakeholders in an ongoing dialogue. We need to bridge the gulf between water managers and water scientists and engineers to ensure that the perspectives of each inform the other. So let me illustrate this with a true story that occurred a few years ago on the Pine Ridge Indian Reservation in South Dakota. The hydrologist was explaining the results of an aquifer test to the tribal council of the Oglala Sioux tribe. A well had been drilled into the Rickaree Formation near the town and pumped continuously for 7 days. The well yield was estimated at 450 gallons per minute, one of the largest well yields ever reported for this aquifer. The hydrologist proudly explained that this was a very good well, and his well yield estimate was a sustained rate, unlike drillers' estimates that are sometimes exaggerated and based on a short-term surging of the well. Well, at the conclusion of the briefing, a council member spoke slowly and skeptically, posed the question. So, Mr. Government Scientist, I mean, you kind of know you're in trouble. So, Mr. Government Scientist, are you telling us that we can pump this well for as long as the grass shall grow and the wind shall blow? Well, the hydrologist hesitated before answering, well, we didn't pump it that long, realizing he'd just been given a lesson on time scales and what is really meant by sustained yield. Language is going to be important in this dialogue. We're going to have to communicate clearly. So it's clear, I think, that science and technology can benefit from a broader perspective. Furthermore, research must be conducted in new ways that readily support management, but at the same time maintain independence and objectivity. This is a tricky challenge that we have, not just in this area of natural resources, but in every area, I think, that where science and technology are going to impact things that touch people's lives. We need to be involved in the process. We need to help form policy. We need to be part of this dialogue with the public, which is two-way, means speaking and listening. We need to do all that at the same time we don't give up at all the integrity of the research process, what we learn, why we believe what we believe, what is the discipline that we use to ensure that knowledge is advanced and not simply the random idea of people's thoughts from one day to the next. That's challenging. Don't think there's any easy answer to that, but I think we need to talk more about it together because it's coming fast. The rate of scientific and technological advancement, essentially across the board, is extraordinary. And it's coming into collision with politics, with people's values, sometimes deeply held ethical, moral, religious values. We have to be a part of that discussion. We're going to have to engage in a way that I think the word dialogue truly describes. If we don't do that, then a couple things happen. First of all, our country, our world misses the opportunity to make these connections and thereby misses the chance to connect science and technology in ways that improve people's lives. But the other thing that happens is you get knee-jerk reactions, negative reactions that shut off the very research process or the funds for that that enable us to go forward. So we have a big job to do together. We do engage in adaptive management. It's often applied to our most vexing natural resource problems, like releasing water through the Grand Canyon, recovery of the Pacific Northwest salmon, and hypoxia in the Gulf of Mexico. But this process of integrating science and technology and management is not yet perfected, so we've got to work at it. I think your expertise in the geosciences and hydrology is needed now more than ever. So I ask you to bring your collective talents to the task of achieving sustainability of our resources, and also recognizing that doing good science and engineering requires funding. So I make my heartfelt appeal to all of my colleagues in science, engineering, and technology to becoming civic scientists or citizen scientists. You may have heard me make the request before, but I encourage you to make your respected and strong voices heard individually and collectively in support of R&D funding for science, engineering, and technology. In addition to being a civic scientist means communicating scientific and technical information to the public as well as your colleagues. so much knowledge being made available every day from all of our efforts and our colleagues that we can't keep up with it. It's very hard for one scientist to understand much about what's going on in even a neighboring discipline. So we have dialogue with our colleagues across down the hall or across the way to try to help everyone understand how science is advancing. But that's not enough. We have to reach the general public, whether it's through our Rotary clubs or our League of Women Voters or our neighbors or our children, our children's teachers. In every way, you get the opportunity. Spend a little bit of time invested in listening and also explaining what it is we do and why it is so important. We have got to impart our understanding of these complex problems of sustainable development as just one example. And I'm very proud that my associate director, my good colleague, my good friend and mentor, associate director for the environment, Rosina Beerbaum, is receiving AGU's award honoring an exemplary civic scientist. So if any of you are curious about how you do it, talk to Rosina. There are enormous challenges and exciting possibilities for science and technology. And even though some may say that the future has no constituency, I would argue all of us have a special duty to ourselves, to our children, future generations, to make these far-sighted investments in research and scientific discovery to build a better America for the 21st century. Because as we hand off the stewardship of our natural resources to the generations that will come of age in the next century, we must do so with the maximum empowerment that knowledge and understanding can provide. The challenge falls to us, this generation of scientists and engineers, to lay that foundation, to choose the correct indicators, to gather the right data, to provide the innovation and incremental advances so that our successors can say they solved some of these problems that we're talking about because they were able to stand on the shoulders of giants, giants like all of you that I've had the great pleasure to be with today. So thank you for what you're doing to make it a better world for all of us and for our children. Good luck for the rest of the meeting. Thank you very much.